All right, so next inequality I'm going to prove using induction is this one. 2 to the power of n is greater than or equal to n squared for natural numbers bigger than 4. So it's kind of, I've done something to the power of n greater than something. I've done n squared greater than equal to something. This is kind of combining the two of them, okay? Same steps as ever. So first one, show, it's going to be P4, it's 4 you're subbing in. Is true, so 2 to the power of 4 is greater than or equal to 4 squared. 2 to the power of 4 is 16. 4 squared is 16. So because I've got the or equal to, that's true. So that's important there. Therefore, P4 is true. Let's, next step, assume. PK is true. So 2 to the power of k is greater than or equal to k squared. Third step then, prove p to the k plus 1. So 2 to the k plus 1 is greater than or equal to k plus 1 squared. So just like when I encountered something like this in a previous example or in any of the induction questions I've done, I'm going to split this up using that rule of indices. So that's the same thing as 2 to the k multiplied by 2 to the 1. It's greater than or equal to, let's just multiply that out. So that will be k squared plus 2k plus 1. Now, I've got 2 times 2k, 2 to the k is greater than this. Up here I've got 2 to the k is greater than this. All right, so as I did in a previous example, as I did in both of these previous examples, I'm going to bring this down, but just like in the other exponential one, I'm going to have to multiply this by 2 when I bring it down so that the left-hand side is the same as the left-hand side here. So from PK, and maybe just note that you're multiplying it by 2 times 2k so that they look the same is greater than or equal to, obviously you have to multiply that side as well so that you're not changing the inequality. So 2k squared. All right, so this is my to prove, and this is my assumed to be true. Okay, so I assumed it to be true and it was like this. I can still assume it to be true when I multiply both sides by 2 because I'm not changing it then. Right, so I am assuming, or let's say I know this is less than this. I'm trying to prove this is less than this. So I know for sure, let's say, this is less than this. So if this is less than this, it must also be less than this. So I'm gonna bringing that in here nearly, and then just looking at that bit. Okay, so my next step is to bring this in here and say this is less than this. So 2k squared is greater than or equal to k squared plus 2k plus 1, so true. If now let's get everything over the same side greater than or equal to 0. Let's get a quadratic and see if that does anything for us. So let's bring everything over to the left hand side. So 2k squared here. If you bring the other k squared over, you're just left with k squared minus 2k minus 1 is greater than or equal to 0. So where my head might go to here is factorizing this. Actually, guide number wouldn't work here. So I think I put another proof of this up that's done elsewhere. What they do, what I've seen done to prove this exact one elsewhere is to complete the square on the left-hand side. Now, I would absolutely do that if this here nicely completed a square for me, because then I'd have something squared is greater than or equal to 0, and that's obviously true because when you square something, you always get a positive answer. But to complete the square here, you need to kind of introduce another number. As I said, you'll see it in something else I post up. So because you introduce that other number, it's not quite as neat. You have to kind of square completed is greater than or equal to something else. So I think it's fine here to actually bring the -1 over. So to say k squared minus 2k is greater than or equal to 1. And then factorize k out. So k on k minus 2 is greater than or equal to 1. And then remember, what is important here is that I would get k greater than or equal to 4. Okay? What would throw up an issue for me is if this was only true for k greater than or equal to 5 or 6 or 7 or something like that. So is this true for k is greater than or equal to 4? Well, let's sub 4 into it. 4 on 4 minus 2 is greater than or equal to 1. 4 times 2 is 8, which is obviously correct. Now, 8 is greater than 1, yeah. This k is only getting bigger as you sub bigger numbers in, 5, 6, 7, 8. K minus 2 is only getting bigger as you sub in 5, 6, 7, 8. So there's no way for this number here to get any smaller than 8. So this absolutely is true for k is bigger than 4, which means overall the entire thing is true for n's greater than or equal to 4. So I can just go in with my conclusion. Therefore, Pn is true for all natural numbers greater than or equal to 4. Just, that's natural numbers. All right, so there's a proof. 2 to the n is greater than or equal to n squared. It's worth having a look at. It is mentioned as they kind of give a couple of examples of the types of these you'll have to solve in the syllabus, and they do mention this one specifically, so it's worth having